Hi guys, welcome back. This is the continuation of the two-part video lecture on quadric surfaces. In the first video, we talked about the four central quadric surfaces, the ellipsoid, elliptic hyperboloid of one sheet and of two sheets, and the elliptic cone. We have seen that for those four types of quadric surfaces, the most dominant trace is either an ellipse or a hyperbola, which is a central conic section, hence the collective term central quadric surfaces. For this video, we talk about the two non-central quadric surfaces, the elliptic paraboloid and the hyperbolic paraboloid. Both names contain the noun paraboloid, which actually suggests that the most dominant trace for each type is a parabola. Recall that a parabola is a conic section which does not have a center, rather it has a vertex. Consider an elliptic paraboloid. Shown in the figure here is an elliptic paraboloid with vertex located at the origin, and it opens towards the positive z-axis. Its standard equation is z equal to x squared over a squared plus y squared over b squared. Observe in this equation that exactly one variable is of degree 1, and the two other variables are of degree 2 and have the same sign. In particular, here, both coefficients are positive. Moreover, the constant term is 0. Inspecting the graph of the elliptic paraboloid, we can see that it is also an axial quadric surface. In this case, the axis is the z-axis, which is the variable of degree 1. If we look at the traces on the three coordinate planes, on the xy plane, the intersection of the paraboloid would be the origin. So that is a point. The trace on the yz plane is this parabola, and the trace on the xz plane is this other parabola. So the traces on the three coordinate planes consist of a point and two parabolas. Observe that these two parabolas may extend infinitely towards the positive z-axis. And so we have to cut the surface by a plane that is perpendicular to the axis of the quadric. So we assign a constant value for z, and when we use that plane to cut the surface, the intersection would be an ellipse. So to sketch a skeleton for an elliptic paraboloid, we need two parabolas and one ellipse. And as I usually advise you, we sketch the ellipse first, and once we have the ellipse, you can easily draw the two parabolas. Note, however, that this is just an equation for this particular orientation. There are 5 other orientations for the elliptic paraboloid. You can rotate this 90 degrees towards the positive x or towards the negative x, 90 degrees towards the positive y or the negative y, or you can flip it over. Okay? If you flip it over, that means the vertex is still the origin, but the elliptic paraboloid opens towards the negative z-axis. So you are simply negating the z-coordinate. In that case, the equation would be z equal to negative x squared over a squared minus y squared over b squared. And observe that this equation still satisfies all the conditions stated here, and the two variables of degree 2 now have negative coefficients. For the other 4 orientations, we interchange the roles of x, y, and z. In particular here, we can see an elliptic paraboloid that opens towards the y-axis, and hence, the variable y is of degree 1. Opening is on the positive side of y, so coefficients of the variables of degree 2 are positive. This is an elliptic paraboloid that opens towards the negative y-axis, so that the linear variable is y, and coefficients of the quadratic variable are negative. And finally, here we have an elliptic paraboloid that opens towards the positive x-axis. So linear variable is x, and quadratic terms have positive coefficients. Here we have an elliptic paraboloid that opens towards the negative x-axis. Linear variable is x, negative coefficients for the quadratic variables. Let's look at an example. Here we have the equation z equal to 3x squared plus 3/4 y squared. We are guaranteed that this represents an elliptic paraboloid because one variable is of degree 1, two variables are of degree 2 and have the same signs. Constant term is 0. If we choose the best orientation for the three-dimensional space, say if I want an illustration where the opening is upward, then we look at the axis of the paraboloid. The linear variable here is z. These are of positive coefficients, so we let the positive z-axis point upward. Hence, I can use the usual orientation of the three-dimensional space. Let us look at the necessary traces for the skeleton of the elliptic paraboloid. First, we can look at the vertex. On the xy plane, that is when I set z to 0 in this equation, we have a sum of two squares equal to 0. That equation has solution x equal to 0 and y equal to 0. So we get the point 0, 0, 0. That is the vertex of the elliptic paraboloid. The other three traces that we need are two parabolas and one ellipse. We expect that there is an ellipse somewhere here because the elliptic paraboloid opens towards the positive z-axis. So we assign a positive value for z and solve for the trace on that plane. Let me take z equal to 3. If I take this z here to be 3 and divide both sides by 3, we get the equation x squared plus y squared over 4 equal to 1. This is a standard equation of an ellipse centered at the origin of the plane z equal to 3. So from this point, we measure along x 1 unit and along y 2 units. So 1 on positive x, 1 on negative x, 2 on positive y, 2 on negative y. We get the following ellipse. For the trace on the yz plane, we set x to 0. Setting x to 0, this term vanishes. It leaves us with the following equation. Linear in one variable, quadratic in the other, gives a parabola on the yz plane. Here we can easily sketch the parabola because all we need to do is to use this vertex, and then on the yz plane, you can see that the intersection of this ellipse would be this vertex of the ellipse and the other vertex of the ellipse. So using these 2 points and the vertex of the paraboloid, this is the trace on the yz plane. And finally, on the xz plane, similarly, when y is 0, it gives the equation x squared equal to z over 3. This is a parabola on the xz plane. The vertex is still the origin. And here, if we construct an axis parallel to the x-axis, we can see that the 2 points of intersection is this point and this point. So using these two and the vertex, we get the following parabola. This is the skeleton of the given elliptic paraboloid. Shading for easier visualization. Broken curves indicate the portion cannot be seen from your perspective. Here are some important points on the elliptic paraboloid. And the last type of the quadric surfaces is the hyperbolic paraboloid. You can see an illustration of a hyperbolic paraboloid here whose equation is z equal to y squared over a squared minus x squared over b squared. It actually is similar to the equation of an elliptic paraboloid except for one difference. We can see that one variable is of degree 1, the constant term is 0. Two variables are of degree 2, however, they have opposite or different signs. One is positive, the other is negative. Inspecting these hyperbolic paraboloid, we can see that the axis is the z-axis, which is still the variable of degree 1 in the equation. Looking at the traces on the coordinate planes, so here we can see that the trace on the xy plane would be this line and this line, a pair of intersecting lines. The trace on the yz plane is this parabola, and the trace on the xz plane is this parabola that opens downward. For the traces necessary for the skeleton of the hyperbolic paraboloid, aside from these three traces on the coordinate planes, we have to cut it by a plane above the xy plane and another plane below the xy plane. The intersection with a plane above the xy plane is this hyperbola, and the intersection below the xy plane is another hyperbola. Basically, we need two parabolas and two hyperbolas. We also cut it on the sides using planes perpendicular to the y-axis. Here we can see another illustration for this hyperbolic paraboloid. They look kind of different from each other, but they are actually the same surfaces. We can obtain the figure on the left by cutting the figure on the right using a plane above the xy plane. So if I assign some value for z here, if you draw a plane here parallel to the xy plane, the trace would be a hyperbola, exactly this. Okay? But usually, I use this to illustrate a skeleton for the hyperbolic paraboloid. And again, this equation is just one of the 6 possible equations for the hyperbolic paraboloid. You can have 5 other orientations for this, depending on the axis. Here we can see that I interchange the variables x and y. I now have the equation z equal to x squared over a squared minus y squared over b squared. It means that we are taking the same axis for the hyperbolic paraboloid. However, the parabolas interchanged their orientation. So now we can see that the graph is the mirror reflection of the previous one with respect to the xy plane. The other 4 orientations are as follows. Here you can see 2 hyperbolic paraboloids with axis the y-axis. That is because y is the linear variable. This orientation gives us a parabola that opens towards the positive y-axis located on the yz plane. Hence, the z variable here has the positive coefficient. This one has a parabola that opens towards the positive y-axis but located on the xy plane, and hence the variable x has the positive coefficient. These two are hyperbolic paraboloids with axis the x-axis because the linear variable in the equation is x. This is a parabola that opens towards the positive x-axis and is located on the xz plane. Hence, the variable z has the positive coefficient. While this has a parabola that opens towards the positive x-axis located on the xy plane, and thus the variable y has the positive coefficient. And again, if you compare all 6 orientations, the nicest looking orientation would be the first illustrated hyperbolic paraboloid. Let's look at an example. Suppose z is equal to y squared minus x squared. This represents a hyperbolic paraboloid because one variable is of degree 1, 2 variables are of degree 2 with different signs. Moreover, because the linear variable is z, that means the axis of our hyperbolic paraboloid is the z-axis. So I am going to take the z-axis to be the axis pointing upward. Moreover, here, if I want the first orientation, that means I want the parabola on this plane to open upward. Thus, this plane here must be the yz plane. So I am using the usual orientation of the three-dimensional space. So for the necessary traces, we can begin with the trace on the xy plane. Setting z to 0 here, we get a difference of two squares equal to 0, which I can simplify to either x equal to y or x equal to negative y. Each of those two equations represent a line. And those two lines actually intersect at the origin. The trace on the yz plane is obtained when we set x to 0. Doing that, this term vanishes, which gives us a parabola on the yz plane. This has a positive coefficient on the quadratic variable, and hence, from the origin, that parabola opens upward. So cut it somewhere here. In particular, I am picking here y to be 2, so that z would be positive 4. Y here is negative 2. Z here is positive 4 also. On the xz plane, we set y to 0. Doing that, this term vanishes. It gives us the following parabola. The parabola is located on the xz plane. And because this coefficient is negative, it opens towards the negative z-axis. We have this illustration. I am assigning here x to be positive 2, so that z here is negative 4. X here is negative 2, so that z here is negative 4 also. For the other traces, we have to cut it somewhere above and below the xy plane. If I assign z equal to 4 in this equation, we can rewrite the resulting equation in the form y squared over 4 minus x squared over 4 equal to 1, which represents a hyperbola. And observe that on this plane, the vertices of this hyperbola will be on y equal to 2 and y equal to negative 2. So from this point, we measure 2 units along y, that is exactly this point, and 2 units along negative y, that is this point. And the branches of that hyperbola on the plane z equal to 4 will open towards the positive y and towards the negative y. On the other hand, when I take the trace on z equal to negative 4, I will get this particular hyperbola. This time, from z equal to negative 4 here, the vertices will be located along the x-axis. So we measure 2 units on positive x and 2 units on the negative x. From this point, the branch will open towards the positive x, and from this point, the branch will open towards the negative x. We have those 2 hyperbolas. And finally, we cut somewhere here and somewhere here. We assign constant values for y, 1 positive and 1 negative. In particular, if I assign y to be positive 4, we get the following parabola. If y is negative 4, we get this parabola. Both parabolas will have their vertices at the point where z is equal to 16. However, z is equal to 16 is already above the plane z equal to 4. So that means when we sketch those 2 parabolas, we won't be reaching the vertex. Okay, so we have to cut this on z equal to 4. This would be the illustration of the given hyperbolic paraboloid. Shading for easier visualization. Broken curves for portions which cannot be seen from your perspective. And finally, label of some important points on the graph of the hyperbolic paraboloid. So that completes the 6 quadric surfaces. We end the lecture by considering translated quadric surfaces. That means for a central quadric surface, the center may not be the origin, but a point HKL. Or for the non-central quadric surfaces, the vertex may not be the origin, but the point HKL. In that case, in the equation, x, y, and z are respectively replaced by x minus h, y minus k, and z minus l. Did you know that we can actually summarize all the tips I gave in the previous examples in 2 easy steps. First, you identify the best orientation of the 3-dimensional space and you construct the axis. And second, you sketch the quadric surface. Charan? Okay, it's quite not funny, but let's proceed. Here are some tips for sketching a quadric surface. First, you identify the type of quadric based from the given equation, and you choose the best orientation of the coordinate axis, preferably one that gives an upright position of the surface and minimizes depth. Recall that an upright position is attained when you choose the vertical axis as the axis of the quadric. For central quadric surfaces, that is the variable with the different coefficient, different sign, while for the non-central quadric surfaces, that is the variable of degree 1. Next is to determine the traces needed for the skeleton of the surface. And finally, you sketch those traces, and if possible, if there is an ellipse, you draw the ellipse or ellipses first. Let us now consider an example of a translated quadric surface, and let us use these tips to sketch the quadric. Consider x minus 5 squared minus 6y squared minus 3 halves z squared equal to 1. Observe that in the equation, all 3 variables are of degree 2. 2 of them have negative coefficients, and the constant term is 1. From these observations, we can tell that the given is actually an elliptic hyperboloid of 2 sheets. Furthermore, there is a translation. We can see that there is no translation in y and z, but there is a translation in x. So instead of just an x here, we have an x minus 5. So that h is equal to 5, which means that the center of this elliptic hyperboloid of 2 sheets is the point 5, 0, 0. Furthermore, the variable with a positive coefficient is x. Okay? And so we take the vertical axis to be the x-axis. Constructing that in the 3-dimensional space, vertical axis is x. We can take this axis to be z, and y will follow from the right-hand rule. For the necessary traces, we observe that the center is the point 5, 0, 0. And since we are expecting an elliptic hyperboloid of 2 sheets with this axis, then one branch, or one sheet rather, opens towards the positive x, and the other branch opens towards the negative x. Let us consider the trace on the yz plane. The yz plane has equation x equal to 0. When I set x to 0 here, the remaining term negative 5 will be squared, and when the resulting equation is simplified, you can check that we can rewrite it in the form y squared over 4 plus z squared over 16 equal to 1. On the yz plane, this is an ellipse with center at the origin. Vertices are located on z equal to 4 and negative 4, so that will be somewhere here and here. And other 2 points are on the y-axis, 2 and negative 2. So 2 on y and negative 2 on y. So this x value is equal to 0. That is 5 units from the center. And 5 units from the center above is x equal to 10. So taking the trace on x equal to 10, that will give you this equation of the ellipse, which clearly is of the same size as the ellipse we obtained on the yz plane. So you just translate this ellipse 10 units upward, we get this trace on x equal to 10. Aside from these 2 ellipses, we expect that the other 2 traces are hyperbolas. Let us consider the trace on the xz plane. The xz plane is obtained when y is equal to 0. Setting y to 0 here, we get this equation, which represents a hyperbola. Here we can see that the denominator of x minus 5 squared is 1. So that means the vertices of this hyperbola are located 1 unit from the center of the quadric. So 1 unit above 5 is 6, and 1 unit below 5 is 4. So from x equal to 6, we connect this to the vertices of this ellipse. And from x equal to 4, we connect with the vertices of this ellipse here. So we have this hyperbola. And finally, on the xy plane whose equation is z equal to 0, we will get this hyperbola. That will have the same vertices as the previous hyperbola. And you connect this point here with the other 2 points on this ellipse and this vertex with the other 2 points on this ellipse. So we have this hyperbola. Shading for easier visualization, dashed curves or broken curves for portions which cannot be seen from your perspective. That concludes the lecture for quadric surfaces. Thank you.